Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video on Math Basic course. And as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Stepping inside as we explore section 1.2 in the Big Ideas Math Integrated Math 3 textbook on modeling with volume. So we just did modeling with area and it had to do with population density a lot. Now we're going to do a lot with just density. Just the general phrasing, and hopefully this lecture and stuff will be faster. It's only 15 problems, actually, if you will. I guess that this first intro chapter really just has a few things to touch on, and then it moves forward into the algebra, like I said before. Following this will be a 1.1 to 1.2 quiz review, which I'll make sure to get that video up in just a moment. But if it's not up yet, hold on tight. Otherwise, jump to the description section down below. You can download this PDF as well as taking a look at the timestamps for each part, including the lecture and then the problem set, which we do. So without further ado, guys, I'm going to go ahead and get started. Let's take a look at what we'll learn. Use volume formulas to find densities and to solve problems. Now, density is the new phrase with volume and square root. We did do square root for a couple problems before involving radius, so that shouldn't be only revisiting now. But volume is in there. And there are different formulas for volume we'll be sure to touch on. Since we just saw population density, guys, density isn't really much different. It just depends on how you really see it. Because we're not talking about people anymore. And area, now we're talking about mass and volume. How much you occupy heavily divided by how much space there actually is. It's the amount of matter in an object has in a given amount of volume. So that's our calculation. Different materials have different densities, so density can be used to distinguish between materials that look similar. For example, table salt and sugar look alike. Very true. However, table salt has a density of 2.16 grams per cubic centimeter, while sugar has a density of 1.58 grams per cubic centimeter. I hope that's not something we have to remember. If so, we'll have to go back to this page because I did not know that. I will not remember that. All right, using formula for density, first example. Let's take a look at this thing. Is that butter? The diagram shows the dimensions of a standard gold bar. Very, very close. They're about the same thing. At Fort Knox, gold has a density of, and again, I guess they have to tell you these, 19.3 grams per cubic centimeter. So they're telling you density right now. That is the mass over volume. 19.3 grams every 1 cubic centimeter, which is indeed the volume in that case. Find the mass of a standard gold bar to the nearest gram. So 1 gold bar with this in mind. Okay, so we're going to have to figure out how many cubic inches this thing is in terms of volume. We're going to have to convert cubic inches to cubic centimeters as we do all that. Oh, looks like they're going straight from inches to centimeters straight up. So 1 inch is 2.54 centimeters. I think that's one we are going to have to know. Like, I don't know if they're going to ask us questions on that. That's something that I know, and I feel like that's something that we'll have to kind of see. Anyway, they go straight from inches to centimeters, straight up. Sounds good. So they convert these, and I guess that's exact. And they get this many centimeters for each. So they can multiply length, width, and height to get the volume of 1 gold bar to get 163.70935. 727.69 cubic centimeters. Looks like that's approximated. So finding out the mass of 1 gold bar, knowing the density rate right here, density equals mass over volume, they're going to multiply both sides by the volume. And they get 14,044 grams approximately there. So given that, here's why we had to convert to cubic centimeters. Because the density rate, I guess, the density that you have is grams per cubic centimeter. Grams are already applied. So we know it's going to be grams, and we were in inches. We need centimeters to make cubic centimeters to follow along with this. Otherwise, we would need a different rate for density regarding cubic inches, which we don't have there currently. Okay, there's that one. Let's skip the one below before we get to the problem set. Let's look at example 2 using a volume formula. A tree harvester is often interested in the volume of a tree's trunk because most of the wood volume is located there. A tree harvester estimates the trunk of a sequoia tree to have a height of about 50 meters and a base diameter not radius, of about 0.8 meters. The wood of a sequoia tree, part A, the wood of a sequoia tree has a density of about 450 kilograms per cubic meter. Find the mass of the trunk to the nearest kilogram. Before we do part B, let's take a look at part A, just because that's a lot that's written, and I don't want to forget what we just talked about here. So the wood has density of 450 kilograms per cubic, Find the mass. We got to first find the volume of this tree with a height of 50 meters and a diameter of 0.8 meters. Now the volume of a cylinder, which is what a tree trunk essentially is, of a cylinder, we're going to have area of base times height. pi r squared times h. So radius is 0.4, which is half of 0.8, and we compute that. And I honestly would leave the 8 pi as it is before I don't want to round early. But it's about 25.13 cubic meters. And now we have our mass over volume working itself out again. A word problem. I guess last one was a word problem. But we find the mass this way. And this mass, before I look at their answer, was kilograms. So they're saying find the mass of the tree trunk to the nearest kilogram. So same thing is applied here. So we're going to multiply both sides by 2, 5.13. Again, I would use 8 pi. And we get around 11,309 kilograms for the mass of the tree trunk. All right, part B, I didn't read it yet. Each year, the tree trunk forms new cells that arrange themselves in concentric circles called growth rings. Yeah, so I guess within here, you would see some. Excuse me. These rings indicate how much wood the tree produces annually. The harvester estimates the trunk will put on a growth ring of about 1 centimeter thick, and its height will increase by about 0.25 meters this year. How many cubic meters of wood does the tree trunk produce after 1 year? If the tree grows at a constant rate for the next 5 years, will it produce the same amount of wood each year? Explain. Well, the answer to that last part should be no, just because of how this thing expands outward. But I'll let them answer it, of course. But the second part, we just got to add 1 centimeter to the overall tree trunk will put on a growth ring of 1 centimeter to the overall 0.8 meters here. Remember, this is diameter. We'll take radius of 0.4 meters, which is 400 centimeters. Is that right? No, 40 centimeters, and we'll add a centimeter to that. So that'll be 0.41 radius, centimeter radius instead of 0.4. Oh, 0.01. 0.01. Okay, I gotta think of my unit conversions. I'll get to that later. Anyway, so 0.41 after that, its height increases 0.25 from the original 50, and then we're going to go ahead and take that volume and do something with it. You see it there. And then it looks like as they computed more volume things here, it shows how you're adding different amounts each time. Therefore, there is not the same amount of wood constantly added year after year, because they do the same thing, another 0.25, another 0.01, another 0.25, another 0.01, etc. And it looks like there's a different amount of volume where you're adding more. You're adding more than you did the previous time. So the tree will not produce the same amount of wood each year for 5 years because the differences in volume from year to year are increasing. Now, did they ask to get the mass here? Let's see, part B. They just said how many cubic meters. They didn't ask for anything regarding density on that question. It was just using volume itself. So area of base pi r squared times height will give us that volume each time, and that's what they do. Okay. All right, using a volume formula. Before a winter storm, a pile of road salt has the dimensions shown. Okay? It's a cone, by the way. After the storm, the linear dimensions of the pile are half of the original dimensions. I guess it blows away. How does this change affect the volume of the pile? I know it's going to be 1/8 of what it was because volume, you take the cubic amount thing, but they're going to compute both. And then part B. Okay, let's start with part A. Now it should be 1/8 of what it was, I think, if all goes well here. So first of all, this is a cone, right? By nature, volume of a cone is 1/3 area of base times height. Not this height here of 53, but this height here of h. So they're gonna have to find out. And this diameter is 90, which means this guy's 45. They're going to have to use the 45 and 53 to find out what this height is here. So they're going to use a Pythagorean theorem setup to do that. Looks like we're getting exactly 28 from that. So it's an a squared plus b squared equals c squared kind of setup. Now they're going to solve for h to get, here's a drawing, perfect. They're going to use a drawing of h to get 28 from that. And 1/3 area of base is pi r squared, pi times 45 squared. And then times that height of 28, and you get values out from that. So this one's 18,900 pi cubic feet. So they didn't round by multiplying by pi here. They left it in terms of pi. And then after the storm, they make the radius half of what it was, the height of half of what it was. And then they're going to get this number here. That's exact. And then they divide one by the other, and here you get the 1/8 that I was referring to. If you take all three-dimensional lengths, both dimensions of radius and dimension of height, take half of each of those, that becomes 1/8 as a whole. That's why I said that answer. So let's look at part B. A lane mile is an area of pavement that is 1 mile long and 1 lane wide. Okay? During the storm, about 400 pounds of road salt was used for every lane mile. I didn't know that. Anyway, Estimate the number of lane miles that were covered with road salt during the storm. A cubic foot of salt weighs about 80 pounds. There's a lot to unpack, even for me, with these things. I go like, which part do I have to draw? What do we have to state? There's a lot of unit conversions as well. So give me a second to kind of look at what they're asking. I know they're going to answer down below, but I need to really understanding what they're going to say. So during the storm, 400 pounds of road salt was used for every lane mile. Now, a cubic, so here's your density that you have here. 80 pounds for a cubic foot of road salt. So that's the density portion is 1 cubic foot, 80 pounds per 1 cubic foot. Mass over volume, right? 80 pounds per cubic foot. So we use that to come up with, and we have 400 pounds of salt. We have that mass. We're going to use that mass with this to come up with the overall volume of it. So, okay, let's go down to that now. During the storm, they said during the storm. Hold on. Estimate the number of lane miles were covered during the storm. So anything that was remaining or lost in area pavement, hold on. During the storm, about 400 pounds were used for every lane mile. So I guess what was lost. So they take away from the original to the new. So this is how much was used for it. Because they take that away. All right. Anyway, that's something I'll have to make sure that I'm really good at when we do a problem like that. So now we do, well, okay, they're doing a unit conversion. That's right, because they're doing cubic feet here and they got to convert it to pounds. So 80 pounds per 1 cubic foot's the density there. And then this is that mass. And then they convert it to lane miles as well. They're 400 pounds for every 1 lane mile. So they do this. Now, they're writing it in a ratio sense. I'll probably do it as a proportion with you guys. This first one actually worked out fine if you do it as density. You can just say density equals mass over volume. Oh, they have mass. 80 equals, no, they have volume. Mass over volume. Like that, and then you multiply both sides by it. That one's the density formula straight up. This one's probably more so a conversion thing. You can use it this way, but I might set up a proportion to work it out in a way that you've probably seen before. Because they're converting pounds to lane miles because they're 400 pounds for every 1 lane mile. And so they get 10,390.82 lane miles, about 10,400. It looks like they did some serious rounding there. So that's kind of a lot to unpack with that one problem in parts A and B. I'll try and walk through a problem with you a little bit better if you had trouble with that lecture portion on it. All right, so yeah, that one last problem kind of took the wind out of my sails when it came to time, but now we're going to go ahead and go to the vocabulary and core concept check before we hit numbers 3 through 15. So what do you obtain when you multiply an object's density by its volume? Well, think about this. Density is mass over volume as a formula. So when we go ahead and multiply density by volume, we indeed get mass. So we obtain object's mass. Now we just saw that literally with that last problem, the salt, whatever stuff, right? We obtained the object's mass. That's your answer. That's your answer to number 1. Okay, number 1. Number 2, which is different? Find both answers. So what is the mass per unit of volume? Now I'll mark that as an A, but that's in reference to mass per, that's a measure of density. So that's a density question. Let's look at this one. What's the mass divided by the volume? That's also a part A with regard to density. What's the mass in kilograms? That just sounds different. That just sounds like asking for mass itself. That's a mass question. What's the density? That's another part A, asking density. So this is different. That's just asking mass. These are rates of something. Mass per volume, even though this is a unit density. I don't know if that's what they call it. And then this is whatever it's divided by. It's still the same ratio. All right, guys, we're going to dive into the main core problem set now. Grab your calculators, grab your binder paper, print out this PDF, whatever it is you need. I'm going to go ahead and get started. Let's start with this. Number 3. A piece of copper with a volume of 8.25 cubic centimeters has a mass of 73.92 grams. Well, we can get density out of that. A piece of iron with a volume of 5 cubic centimeters has a mass of 39.35 grams. We can get density out of that. Which metal has the greater density? Well, that's what they want us to know. So let's find the density. Let's do this. let's say the mass of copper, volume of copper is 8.25 cubic centimeters, and then mass of said copper is 73.92 grams. We also have volume of iron, which is 5 cubic centimeters. It's not about how much, right? This is more volume than this, but when you divide it from density, it's going to have a different, possible effect. M sub I here, we got 39.35. Looks like this is going to have lesser density, I believe, if I think. All right, so density of copper will be mass over volume, and density of iron will be mass over volume. Okay, let's divide those two. Calculator ahoy. You won't see what I type. I'm just going to get it done. 73.92 divided by 8.25. So we're getting exactly 8.96 for density of copper. That is, and these are compared with the same, things as cubic centimeters, or grams per cubic centimeter, grams per cubic centimeter for that density. And this density, I should be able to do that one in my head, but I ain't gonna. 7.87. Not much less, but. All right, which is greater density? Copper. Copper has greater density, packs in more weight per volume, per unit of volume. Copper has more density. All right, that is but one problem where we compared those two things. Okay, that's number 3. Number 4. Problem solving. The United States has minted $1 silver coins called the American Eagle Silver Bullion coin since 1986. Each coin has a diameter of 40.6 millimeters and is 2.98 millimeters thick. We're thinking cylindrical, right? It's kind of, for this number 4, we're thinking it's like not much height to them or whatever, thickness to them. Whoopsie. But it's cylindrical in nature, right? That's what we're looking at. So something regarding volume of cylinders. The density of silver is 10.5 grams per cubic centimeter. What is the mass of an American Eagle Silver Bullion to the nearest gram? So we got to figure out this volume. We have 40.6 millimeter diameter, mm, and then this thickness is 2.98 millimeters. So the volume, we need to find out radius. Radius is 40.6 over 2, which is 20.3 millimeters. So let's now figure out the volume of this guy here, which will be area of base, pi r squared, times height. So let me do that with the calculator. I'm going to leave it in terms of pi to have that exact effect going on. So 20.3 squared times 2.98. And let's leave the pi kind of out of that. So we're getting 1,228.0282 pi cubic millimeters of volume. Now, density equals mass over volume. We need to find mass based on density. The density of this object is 10.5 grams per cubic centimeter. Okay, I made an uh-oh here somewhere just a little bit because this was millimeters and I need centimeters out of that. So let's kind of change that one a little bit. I think it's just going to change the decimal here. So there are 10 millimeters in 1 centimeter, correct? If they're 10 millimeters in 1 centimeter, then the radius is 2.03 centimeters. This guy is 0.298 centimeters. We're just dividing everything by 10. So I need to take these decimals and move them 1 over here for each of those, which I do believe means when we take this whole nugget here, but it's squared. Okay, we're going to be shifting this decimal quite a bit. So let me do this again. 2.03 squared times 0.298. So this time, instead, the decimal is actually right here. Let's do it in terms of cubic centimeters now so we don't make a mistake later in what that is. So this is cubic centimeters. And that's why it's so important to write out what these things are here. There we go. So this many cubic centimeters, it's still the exact same number right there with pi. It's just shifted, you know, a few places over. 1,000 times smaller, if you will. So we're going to say 10.5 equals, and they want it in grams? Yeah, to the nearest gram. The mass over this volume. And yeah, I'm not going to round early here, guys. That's exactly what this thing's going to be. So mass is going to be 10.5 times that. Multiply both sides by that value, 1.2280282 pi. All right, let's see what we get. Times pi times 10.5. So I'm getting around 40.5. I'll show you in the calculator here. Getting around 40.5 masses, grams. 40.5 G's of mass of the silver bullion coin. Is it American? American silver bullion? Okay, so that's the value I'm getting for that guy. And yeah, once we converted to that thing, then that's how it's going to change, you know, the answer there. Forgot what else I wanted to say to that. I think that's it. Okay, so let's move forward. Let's take a look at number 5. Error analysis. Describe and correct the error in finding the density of an object that has a mass of 24 grams and a volume of 28.3 cubic centimeters. So they did volume over mass. I mean, that's it. Cubic centimeters per gram. We need grams per cubic centimeter. It's not that they have a wrong statement made. That's just not density. It's not officially density. Density is mass divided by volume, not the other way around. That's it. It's not that they miscalculated, they just have their formula kind of backwards. So if the volume is 20, or if the mass is 24 grams right here and the volume is 28.3 cubic centimeters, we're going to flip that guy. So this is going to be a number less than 1. 24. 0.848. I'll use 3 things. 0.848 grams per cubic centimeter. What was this even of? Oh, just objects. They didn't say. Okay, yeah, that's it. Okay, number 6, problem solving. Back to problem solving. The height of a tree trunk is 20 meters and the base diameter is 0.5 meters. So this, already looking at this part A and B stuff, it's going to look a lot like the kind of problem that we had in the example set. So remember, a tree trunk has a cylindrical nature. I'm not going to draw a tree. I'm just going to draw a cylinder. So we have this for tree trunk, cylindrical. Diameter is 0.5 meters. The height is 20 meters. Now we're going to need to know radius for this. Let's make sure that we're doing it in terms of meters here. Density, 380 kilograms per, yes, cubic meter, and they want kilograms there. So no unit conversions. We're going to stick to what they are. So the radius of this guy is half the diameter, which is 0.25 meters. The volume of this guy, this tree trunk, pi r squared, area of base, times height. Now, 1/4 squared is 1/16, and 1/16 of 20, I can do that. 20/16 is 5/4, so it should be 1.25 pi. Let's see if I get that. 0.25 squared times 20. Aha, 1.25. So let's keep it exact for now. 1.25 pi. This is in, what are we talking about here? Cubic meters. Cubic meters. And we have density. We have density of this guy. Let's kind of separate these problems. Density of this guy is 380 kg per cubic meter. Okay, so let's find the mass to the nearest kilogram. So 380 equals mass over 1.25 pi. You've seen it before. I'm going to multiply 380 by 1.25 pi, so I'm skipping that work, and let's just go ahead and calculate it. So you don't round early. Let's keep that pi thing here until you multiply now. 1492, Columbus would be proud. 0.25, I'll just say about 1492. Keep it in Columbus terms. 1492 kilo. Oh, they did say to the nearest kilogram, didn't they? So, yeah. 1492 kilograms. In fact, on the previous problems, did they say to the nearest something? Oh, they said to the nearest gram for this on number 4. Did I answer it that way? I did not. I said 40.5. Let's say 41 grams. Sorry about that. All right, I'll round based on their statements. My bad. Let's go back. All right, that's part A, though. That's part A of this problem. Now, part B, on number 6, they are asking, the trunk puts on a growth ring of 4 millimeters, and its height increases by 0.2 meters this year. How many cubic meters of wood does the tree trunk produce? The tree grows at a constant rate for the next 5 years. Does the tree produce the same amount of wood each year? Explain. This answer should be no on the second part of B, just like it was in the example part. But we're going to go ahead and get all the values out from here. Now, first of all, they say the trunk puts on a growth ring of 4 millimeters. Now, 4 millimeters is not in meters right now, right? Now, if you don't know how this works exactly, let's take a look. There are 1,000 millimeters for every 1 meter. Therefore, 4 millimeters is 0.004 meters. Do I have that right? Dividing by 1,000? Well, let's see, how do I say it? 4 divided by 1,000. I want to make sure that's right. Yes, 0.004. So 0.004 meters are added to we want to add it to the radius, right? So now the new radius of this after 1 year, R sub 1 I'll call it, is 0.254. We're adding the 0.004 to the 0.25 as we do that. Now the new height of this object is going to be just adding 0.2 meters to the 20 meters. So 20.2 meters. So volume of this object 1. And they only ask for volume, not density. It's, again, a lot like that example problem. So how many cubic meters does it produce? So we're going to do pi r squared times height, which is about, this is why going exact is going to be a nice venture here. Did I find the other one yet into 1.25 pi? So let's leave this one in terms of pi. 0.254 squared, so it's not going to be approximate, I'll get the exact, times 20.2. Well, equals exactly 1.30322232. Now listen, I'm very low on space right here. I'm going to go and copy and paste this, like binder paper lines. I'm going to copy and paste this over to like this next side, if that's okay. So we have that. This is the volume. This is in cubic meters for the volume of 1 year later. Okay. Now remember the first one, this is pi. This is in terms of pi. And I want to leave it exact. This is like year 0, year 1, etc. They said do this for the next 5 years. That's quite a bit to take in. 3, 4, 5. So, let's see where I have room to write all this. So this was 1.25 pi. This is 1.30322232 pi. This is all in cubic is, if that makes sense. So we have to do this a few more times, right? So 2, we're going to be adding another 0.004. Okay, I'm just going to write this one more time. Like R sub 2 is 0.258. And height of object 2 is 20.4 now, right? As far as how that works, this is meters and meters. So now we got what? Volume of object 2 is pi r squared times height. So I'll be doing that kind of each time, right? Maybe I can just write them out loud. Maybe I can just write them on paper right now. 262 squared times 20.6. I can't really think of like a faster way to go about it, because I still got to compute these. So 266 and 20. I keep doing that. Handwritten typos, guys. 20.8 and 5. 21. Okay. So let me compute those. I'll actually show you that so you're not just looking at me like clicking clicking away. So let's go to that. I'll just recall what I did previously here. I'm going to change this to an 8 and this to a 4. And I'll go and write that one down. So this is in terms of pi, by the way. So I'm not multiplying the pi out, if that makes sense. I'm just going to write pi in the answer. So when you see it here, I just wrote this and pi is there. I never did times pi on the calculator. Let me kind of straighten these out. 1, 2, 3, 4, 5. So this is number of years. As these years pass by, this is what we have. I know it's got, excuse me, interesting rounding here, but I think it's important for when I do subtraction to show you how they do compare. Let's get a couple more here. Let's take the previous answer and change it up. So this is 6.2 and this is 0.6. And then we'll do that again for 6.6 and 0.8. Then we'll do it one more time for 7.0 and 21.0, I guess. All right. So, whoops. So the next three that we have are here. So I have 1.4, 1.40664 pi. The pi part won't really matter as far as what we do when it comes to difference. It's really just subtracting those numbers. So 1.4717248 pi. This is really having trouble here. I'm not fitting this very well on my sheet, basically. I probably should have gone column-wise. But 1.4717248 pi. And the last one is 1.5309 pi. Okay, so I have them all written very smallly. The question is, do they have the same difference? Is it a constant amount each year? I mean, I can tell you, I believe the answer is supposed to be no. But now we got to kind of do a separation of, subtraction of one versus the other. So now I got to work that out. Let me kind of pause this, do the subtraction here. Otherwise, this is going to take quite a while. Give me a second. Okay, I've completed my journey. I really should have done this vertically. I apologize. But what you see here, if you can, I'll try and divide them in red, is the split of how much you're adding each time from one to the other here. So this is 0.053 something. This is 0.054 something, 0.056, 0.057, 0.059. Maybe I could have done some early rounding in some cases, but I wanted to get exact ones. Oh, this is in terms of pi, by the way. So these are different figures, so you are adding different amounts, which means it's not a constant rate each time. So the question, does the tree produce the same amount of wood each year? No. No. See differences above. That's my explanation, at least. Yeah, so that was quite a bit as far as just needing to do all those little calculations for the next 5 years. I don't know if they literally stated. They said the tree grows at a constant rate for the next 5 years. Yeah, I guess they just wanted you to check them all out. They really should have checked within a couple, but that works. All right, let's go to numbers 7 and 8, where we describe how the change affects the volume of the prism or the pyramid. So tripling all the linear dimensions here. Now I think I spoke in the example problem set what happens when you take one or all 3 dimensions and you do that. You're going to cube the result. So you triple everything here. 3 cubed is 27. The new volume of this new triangular prism is going to be 27 times bigger. So I'll take my word for it. Let's go ahead and check this thing out. The volume of any prism is area of base times height. Now the area of the base, the base itself is established based on being the non-rectangular thing. In this case, it'll be the triangle. So the area of the base for number 7 is going to be the triangle that we're talking about. 1/2 of its base, 4 times height, 3. That'll be 6 square inches of base area. Whereas the height of the prism itself is 8. It's the difference between the distance between your two triangles. So the volume of this guy is going to be area of base, 6 times height, 8, which is 48 cubic inches. And that's the original volume here. I'll just call it volume 1. Volume 1, area of base 1, height 1, volume 1, etc. Now there's that one. Volume 2, meanwhile, is going to be tripling everything that we have. So area of base 2 times height 2, that kind of thing. Area of the second base, now we're going to take our dimensions and triple them. So 1/2 base length 4 tripled is 12 times height 3 tripled is 9. Half of 12 is 6 times 9 is 54. So 54 square inches compared to the 6 already. You can see it's 9 times bigger. And now we're going to be tripling this height as well. We're going to take that 8 and make it 24. And now we have a new volume, area of base 54 times height of 24. Can't tell you what it is off the top of my head. I know it's going to be 48 times 27. 54 times 24 gives me 1,296 cubic inches. So yeah, when you compare, I'll call it K, if you will. It's technically K cubed. K cubed is going to be taking 1296 and dividing by 48. You can see that's where we're going to be getting. I'll just leave it up to, I'm not going to calculate it. It's 27. So 27 times bigger. When you triple everything, when it comes to any volume. 3 dimensions being tripled. 3 times 3 times 3. Okay, that is number 7. Number 8, we're taking a pyramid, multiplying the height by 3 halves. If just the height, one single dimension gets affected, 3 halves is also 1.5, by the way, then the entire volume is going to be 1.5 times bigger. So I'm previewing your answer before you get the answer itself. But let's figure out how to find the volume of a pyramid. This is a rectangular pyramid, and the volume of any pyramid is 1/3 area of base times height. So object 1 is 1/3 area of base times height. Now, we're not going to be changing this area of this base as we do this a second time. The area of the base is length times width, 18 times 12, which we get 216, I think. 216 square centimeters. The height of this object initially is just 14. Now, to find the volume of object 1, pre-height change, we're going to do 1/3 of 216 times 14. 216, a third of 216. Come on. 72. I don't know, 72 times 14. Might as well work that out. 72 times 14. 1,008. So 1,008 cubic centimeters of the orig. Now, the second volume here is based off the new height. The new height is going to be making it 3 times larger than what, or 3 halves this thing of what it was. 3 halves of 14 is 21. So now we're going to be just taking 1/3 of 216 times, instead of 14, it's 21. So only one part becomes 1.5 times bigger, which means this whole volume is going to be 1.5 times bigger. So let's do 1/3, well, I should know 1/3 216, but I already started writing it, times 21, and we're getting 1512. 1512 cubic centimeters. Now, when you compare these two, this K cubed, if you will, I don't know if you call it scale factor here because it's not changing every bit of dimension, but I'm just going to compare this way. 1512 divided by 1008, that reduces to 3 halves. 3 halves times bigger. You can say 1.5, but they used a fraction at the time, so I'm going to use a fraction as well. Yeah, just 3 halves the size of what it was. Okay, number 9, problem solving. A conical pyre of road salt has a diameter, yeah, they're really going based off those examples we had before, has a diameter of 112 feet and a slant height of 65 feet. So it's best that we draw something like this. So we're looking at some road salt. Look at that. Beautiful road salt. We got a diameter here of 112 feet. That's a lot. And a slant height of 65 feet. Slant height is this guy right here. Not used in volume, but will be used to help us find volume. After a storm, the linear dimensions of the pile are 1/3 of the original dimensions. Now, 1/3 of 65 is not a pleasant number as far as I'm concerned. 112, also not very pleasant. So they're not going to give us pleasant numbers for this. Let's start with the volume of this first before we go to anything else. I got to find out this height. This height by using this radius. Half of 112 is 56. Hopefully this height will be a pleasant value. Let's find out what height is. H squared plus 56 squared equals 65 squared. Oh, it should be. This is a 5, 12. Oh, wait, hold on. Is that? 13 is 5. Actually, this might not be. 56 squared. Let's see. 65 squared minus 56 squared is going to give us 1,089. So H squared is 1,089. Probably not a perfect square there, is it? Oh, it is 33. I misconstrued something. Maybe I don't know this Pythagorean triple. So 33 feet for this guy. So let's just start off with the volume here. It says, how does this change affect the volume of the pile? I think they want us to compute the things. If not, we might still have to compute them anyway for part B. So I'm just going to go and still figure it out. Volume of a cone is also 1/3 area of base times height, but this area is specifically pi r squared. So pi times 56 squared, and times its height of 33. Not 65, but 33. Now, I'm going to leave it in terms of pi, even though there's a 1/3 here. Well, let's do this. Oh, I can do that. Yeah, 1/3 of 56 squared times 33. I'll kind of keep the pi in the answer. So volume for now is 34,496 pi cubic feet of the original guy. Okay. Now what we're going to do with this original guy is we're going to take 1/3 of everything, which again is not pleasant when it comes to numbers here. 65 over 3 doesn't reduce. So 65 thirds of a foot. Diameter, which we got to divide that by 2 eventually, that's 112 thirds of a foot. No, 112 doesn't divide by 3. 111 does, but not 112. So yeah, we're dividing these by 3. So the radius that we're talking about, we got to divide that by 2, and that becomes 56 over 3. All right. Height. Well, here's the good news when it comes to Pythagorean theorem. The height will also be 1/3 of what it was. So Pythagorean, we're going to get 11 for that one when it comes to height. So okay, that's good, I guess. I don't know if when it comes to volume, I'll have to deal with fractions, I guess, So volume of this object, this is volume 1. Let's go volume 2. Volume 2 is going to be 1/3 area of base. Boom, pi r squared times height. This one's going to be more of a fraction basis here, and I'll tell you what. Let's do this. 56 squared times 11 is the top. So it's still 34496. 34496 pi. But this is divided now by 3 times 3 squared, which is 27. I guess I should have known. Well, I knew that as far as how this is going to change, how they compare. If one's 1/3 the other one, when all the lengths are thirded. And I don't believe that can reduce. Now, when I divide it straight up, it gives me a weird decimal as a fraction. It's, it doesn't reduce as a fraction. So there's one versus the other. When I divide one versus the other, you're going to get one is 1/27th the size of the other. How does this change affect the volume of the pile? It becomes 1/27th what it previously was. Right? The linear dimensions of the pile are 1/3 of the original dimensions. So volume 2 over volume 1, I'll write it that way, is going to be 1/27th of what it was, right? One of them is 27 times smaller of original pile. So that's how I'm going about answering part A. I'll just say part A, boom. And that's kind of all I can do with that part A as we just refer to it. Now part B. During a storm, 350 pounds of road salt was used for every lane mile. Estimate the number of lane miles that were... So this is like the example thing that we had. I have to kind of retrace what we did. Estimate the number of lane miles that were covered with salt. How many lane miles can be covered with the remaining salt? A cubic foot of road salt weighs about 80 pounds. So there are 2 questions here. The first one is the number of lane miles covered with salt. Excuse me. I think that is what they did on the last time they did it. I think that's what the one that the storm blew out. So the amount that's not used. So like we can take the difference between our numbers from before. So it's good we have both. So we can do 34,496 pi minus 34,496 pi over 27. Basically, we're taking 26/27ths of what we had before. Excuse me. Let's see if there's a good fraction version of this, though. So I'm going to do 34496 pi. I can do common denominator stuff, but I'm going to see if my calculator can do it for me. Oh, let me take out pi. I want to do this in terms of pi anyway. 34496 over 27. Fraction, please. No real fraction number for this. Maybe I have to wing it. Maybe I have to say, forget it. Let's do it in terms of let's get the number for what it is, and there might be some rounding error, but 104,358.5883. This is cubic feet of what is used when the storm blew everything out. So we're taking 26. This I multiplied by pi. I'm writing as exact as I can here because I'm going to use that, I guess, several times. I'll just use my calculator version of what I have. But we're going to take this number, and we're going to do what with it? A cubic foot of road salt weighs 80 pounds. So if we're going to be doing 350, this is like a density, if you will, but there are 350 pounds per 1 lane mile. And we need to get a certain amount of pounds here and figure out how many lane miles go here. To figure out the certain number of pounds, let me move this down. Figure out a certain number of pounds, we got to convert 1 cubic foot is 80 pounds. So if 1 cubic foot's 80 pounds, this boom is this many 80 pounds. So we got to do 80 times this number, 358.5883. This will give you the number of pounds. That times 80 is the number of pounds we'll get for this thing here, 8348687.066. It's a messy problem. So this many pounds, and if we do cross multiply and division, stuff like that, we're going to end up dividing this number by 350. So x is going to be, number of lane miles is 834,868.7.066 divided by 350. And here we're going to get the number of lane miles for everything that was, I guess, blown over. Divided by 350. We're getting 23853.39. 23,853 point, well, I'll round. So 853 lane miles. For all that was blown over there. Okay, so we have that. That's the first one. Then they say how many lane miles can be covered with the remaining salt. So for remaining salt, I guess what I can do quickest, if you noticed, we took our value first and multiplied by 80. And then we divided it by 350. So the remaining salt is this number here. I'm going to do this times 80 over 350. I think that's the fastest way. So 34496 pi over 27 times 80 over 350. Let's not make it hard. I think we could also divide this by 26. We could also divide that by 26. I'll confirm that kind of both of them work. So 34496 pi divided by 27 times 80 over 350, or 8 over 35, gives me 917, about 917 lane miles. I'm going to check as well to see if 23853 divided by 27 still gives me that. If it doesn't, not 27 over 26. Yeah, same number. Yeah, that many lane miles. Okay, so that's how that one works out. I know it's, I don't know if it worked best as far as what I wrote there because it didn't lay out the organizational matter of answering the first question and then the second question, but that's where it's all covered. So blue is this guy here, and then green is this guy here. I used blue to make green a little faster in the end. And that's number 9. All right, yeah, still a lot of problems. Still a lot to do within problems here. It's not like it's short business, short order. Number 10, how do you see it? The 2 stone blocks shown below with the given densities have the same volume. Which block has greater mass? Explain. So density is mass over volume. They have the same volume. And here we have 2.7 grams per cubic centimeter for granite. And this is mass over some volume. So its mass of granite is going to mass of G over volume. Mass of G is 2.7 times some volume V. Now the mass of sandstone, I'll just do it this way. Mass of sandstone is going to be 2.3 times some V. If the V is the same for both, this one that has more density should therefore also have more mass. So, which one has greater mass? Explain. Granite. Granite has greater mass. Granite has greater mass because it multiplies a larger density with the same volume that sand. What was it? Oh, sandstone. That sandstone does. What it multiplies the then sandstone does. There we go. Okay, that was kind of quick. Number 11. A pool in the shape of a rectangular prism is 6 meters long and 3 meters wide. The water in the pool is 1 meter deep. So we have 6 meters long, 3 meters wide, 1 meter deep pool. At least the water is 1 meter deep. I don't know if there's anything about... Okay, yeah. So there's water in the pool here. Looks like we're going to add more to the pool in part B. Okay, so the original 1 meter deep, 1 meter, and then we have 3 meters and 6 meters, right? Yes. The density of water is about 1 gram per cubic centimeter. Find the number of kilograms of water in the pool. Okay, so notice they say cubic centimeters. So 1 meter is 100 centimeters. So each of these, this is going to be 600 centimeters. Let's do centimeters now. 300 centimeters and 100 centimeters. So little unit conversion to begin with. Kind of tricky. So volume of this is length times width times height, right? Area base times height. So 600 times 300 times 100. 6 times 3 times 1 is 18, followed by several zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 18 million cubic centimeters. I trust my own math with that. Density of water is 1 gram per cubic centimeter. So 1 gram per cubic centimeter. And we have how many grams? Oh, kilograms. Let's start with grams. X grams per 18 million cubic centimeters. Therefore, you multiply 18 million by 1, you get 18 million. So X equals 18 million grams. Now, how many kilograms? 1 kilogram is 1,000 grams. So the answer to this is X equals 18,000 kilograms. That should be your final for that guy. Okay, so there's the first part. Part B then asks, what? Whoops. Part B asks, you add 6,000 kilograms of water to the pool. What is the depth of the water in the pool? So now that we have, and I don't know what thing we're using. Meters? I guess we have to go back to meters. We might have to rewind everything from there. So you add 6,000 kilograms. So 18,000. Well, I'll tell you what. If all that's going to change is height, then 24,000 compared to 18,000 should be 4/3 times the amount. So I don't know if I'm allowed to take shortcuts with that. But anyway, 24,000 kilograms. Let's see how I do reverse this in a way that's easy. Because otherwise I don't have to do everything backwards. I don't have to go back to this, that. That's going to be a lot of backwards treading. But let's do it. 24,000 kilograms is 24 million grams, which means 24 million cubic centimeters. We found that out. Okay, I guess that's not going to be a lot. So if the volume is 24 million cubic centimeters and the length and width haven't changed, we're now going to change height here. But check this out. This is where we get that 18 from, but this is 18 that 180,000 times height, and now height is going to be 24 million divided by 180,000, which is going to be, well, it's not going to be a clean number. If I reduce it as like a fraction, well, here, let me just give you the fraction reduction. I believe 400 over 3. Let's go to the calculator on that one. So we're going to have 24 million divided by 180,000. I hope I did those numbers right. 4 zeros with the 18, 180,000. Now this one as a, 400 over 3. So 400 over 3, that's centimeter, or that's centimeters though. So 400 over 3 centimeters, and if there are 100 centimeters in a meter, that'll be 4/3 of a meter. 1 1/3 meters. I don't want to really round that. I want to use the exact fraction thing. Now I would have gotten the 4/3 just by doing 24,000 over 18,000. If the only thing that changed was height, then this ratio here is going to be the same ratio as that one, something that we could have learned there before. So yeah, 1 1/3 meters is now the new height of the thing. What's the depth of water? 1 1/3 meters. Height is depth. Okay, so that's part B. So part A, oh, we already wrote it. That's part B. Okay, let's go to number 12. 4 more questions. A British thermal unit, BTU, is the amount of heat needed to raise the temperature of 1 pound of liquid water by 1 degree Fahrenheit. Kind of reminds me of like a calories thing. There are about 1,000 BTUs per cubic foot of natural gas and about 140,000 BTUs per gallon of heating oil. I'll tell you what, these kind of problems kind of mess me up a little bit. There's a lot of unit conversions, a lot of numbers that they're making me do, and I have to like remember them or utilize them when doing it. So sorry if I act slowly on these. It's my first time seeing them too. Okay. There are 1,000 BTUs per cubic foot of natural gas, and so let's see, 1,000 BTU per cubic foot, and 140,000. I have to figure out where to use these later. BTU per gallon of heating oil. Natural gas heating oil. Okay, let's see where those are used later. Part A. In 2010, electricity generating power plants paid, now we have money, $5.27 per 1,000 cubic feet of natural gas and $56.35 per 42 gallon barrel, whatever, of heating oil. Express the cost of each fuel in dollars per million BTU. Okay, this will take some time for me to unpack. I'm going to say that out loud right now. I might want to pause and even think about it in a second, especially if I get this thing wrong. So $5.27 per 1,000 cubic feet. 5.27 per 1,000 cubic feet. Now we need per 1 cubic foot here, so let's divide these by 1,000, and that'll be, I want to make sure I don't get that decimal placing wrong. I think this is what I want to do. 5.27 divided by 1,000, 0.00527, less than a cent, 0.00527, about half of a cent per 1 cubic foot. And the other one, let's do per gallon for the other one here. So we have 56.35 per 42 gallons. Let's divide that by 42 basically. Excuse me. Let's divide that by 42. 56.35. I don't know if it's going to be a clean number. Not quite. I don't have anything very clean off this one. This is going to be, well, I'm going to round it, but I'm not going to round it in my calculations. $1.34 per 1 gallon. Okay, how do I use those? Excuse me. Express the cost of each fuel in dollars per million BTU per million. Oh, I'm going to have trouble with this. 1,000 BTU per cubic foot. Oh, you know what I could have done? If it's per million BTU, then we could instead have changed the 1,000 BTU to 1 million and the 140 BTU per million. And then that might work out a density in a better way. I'm having trouble with this one here. Because we have the money as well. Let's do... Okay, let me table these ones for a second. Table those ones for a second. Let me look at the other one. 1,000 BTU per 1 cubic foot would also, if I go to 1 million, 1 million BTU, that is per 1,000 cubic feet, basically multiplying everything by 1,000. And I bring that up because we have 1,000 cubic feet in this other one. They paid 527 per 1,000 cubic feet. So that's per million BTU. So that is going to be 527. I think that answer is 527 per 1,000 cubic feet. I think the answer is they paid 527 per 1 million. So equals, this is not good organization work, 527 per 1 million BTU, I think is the answer of the first one. The second one's a little trickier here. When we do the 140,000 BTU per gallon, 140,000 BTU per 1 gallon of heating oil, when I have to change this to 1 million BTU, I gotta do, whatever 1 million divided by 140,000 is, I gotta multiply that weird decimal by that 1 gallon. So this is per 7 point. This isn't a good number, and I should use the fraction instead. 50/7 of a gallon. So this time I am going to resort to fraction. So if they're 50/7 of a gallon there, in here we're going to talk about a 42-gallon barrel. So 56/35 per 42 gallons equals how much money per 50/7 of the gallon, because 50/7 of the gallon is going to be the same as the 1 million BTU, basically. That's how we're working that thing. So what I got to do is multiply both sides by 50/7. So X dollars, I'll just say X. X equals, I don't know if I'm doing this right. X equals $56.35 per 42 times 50/7. And this will be how many dollars per BTU, basically, is my thought on that. So 56.35 times 50 divided by 42 times 7. Let's see. 42 times 50. Guess some rounding's going to be had. This is $9.58 rounded. 9.58 per 1 million BTU is my answer to that. I don't know if that's right, but that's excuse me. That's how I'm going to work that one out. That seems to make most sense with my conversions going that way. I could have used these. I'd have to go back to the number of gallons. I don't know. I think this was just easier to work out this way once I got to the million. Okay, that's my part A. Yikes. If that's part A. Part B. The tank shown can be used to store heating oil. Write a formula for the volume of the tank. Okay, I can do that one pretty well. So with the tank, we have, it's basically divided, well, let's do it here where the radius is. It's divided right there and right there. So we have in the middle a rectangular prism. And then we have two semi-cylinders on top and bottom. The semi-cylinders are the same amount, like lengthwise and stuff, whatever. They're both half the same cylinder, so we could add just one of those in the end. So I have a 2R, let's see, R. So if that length is R here, then this is 2R. So is the height 2R, and that's 4R here. So let's call this object 1 in the middle. And object 2 is considered to be both the top and bottom put together. It's a whole cylinder there. So we have a rectangular prism in the middle. So volume of object 1 is length 2r, or whatever, width times length, whatever, 2r times 4r times height of also 2r. 2 to the 4 is 16. So 16r cubed is object of volume 1. Volume 2 is both things put together. I can do area of base like that circle, pi r squared, literally, pi r squared, and times a height of 4r. This cylinder goes across that way for 4r there. The 2r's actually don't have anything to do with this. So pi r squared times height, and that'll give you 4 pi r cubed. So the volume of the total, because remember it's two semi-cylinders put together there, volume of the total will be 16r cubed plus 4 pi r cubed. Now that is just one version of what we could write. If I wanted to do like a common factor thing, I don't know if this will help or hurt. It might hurt, but if I could factor out a 4r cubed from here, I'd have 4 plus pi, which is kind of interesting. I don't know if that's helpful or hurtful. I'm just writing both of them for now. But that's a good volume of the total like that. Okay, part C, maybe we use that. You pay $3.75 per gallon of heating oil to fill a new tank in which R is 1 foot. So we're going to substitute 1 for R in this scenario. Actually, this might be easier to use the second one in that case. Oh, no, this will work either way. Compare your cost of heating oil in dollars per million BTU to a power plant's cost in part A. How many BTU can be produced from a full tank of heating oil? Oh boy. Okay. Let's get to the nitty-gritty. $3.75 per gallon of heating oil. $3.75 per 1 gallon. So the tank used, we need to write a formula for volume of the tank, and R is 1 foot here. Now feet, volume is going to be 16 times 1 cubed plus 4 pi times 1 cubed. The ones are basically negligible here, 16 plus 4 pi. I don't know if I want to round that here now or later, but that is cubic feet of volume. Did they do something regarding feet and gallons? Compare your costs. Cubic feet. Oh, 1,000. Okay, hold on. You pay $3.75 per gallon. This says of heating oil. BTU. Hold on. I'll find it. 1,000. This is natural gas. This is heating oil. I don't know where I'm going to use cubic feet of heating oil when I have gallons. I don't know how to convert cubic feet to gallons. I'm gonna process this one for a second. Give me a moment to think so I can think about it. I've done a lot of unpacking on this problem, and so there are two parts to this. One which I'm kind of still iffy on. The first part I think I'm better on now. We don't need to talk about the feet to begin with. They're just saying compare the cost of heating oil to what we had in part A. So I can take whatever this rate is and compare it to whatever that rate is there. And I can either do that or work per million BTU that we had. So I can do that as well. We multiply by 57ths for that. So I can take my rate, 3.75 per 1 gallon, dollars per 1 gallon, and multiply that by 57ths, and we get how much you're spending per million BTU, basically. So that number, let's see that. So 3.75 times 57ths, 26.79 about dollars per 1 million BTU. Now we're supposed to compare this to the original amount from part A. Now part A, we were spending $9.58 per 1 million BTU. So I don't know if they mean cost in terms of difference or in terms of times amount. Normally we do that, like 26.79 over 9.58. We can do that. Let's try that and see what we get. This is how many times more we're spending, 2.796, around 2.8. So 2.8 times more money spent compared to the part A. I don't know. My organization of my work isn't always best, and I kind of generally hope in these cases that people aren't relying on me for these problems, at least when it comes to organization. Solving it, sure. But this is where I hit a snag. I'm hitting a snag on the next part. How many BTU can be produced from a full tank of heating oil? Our full tank that we have the volume in terms of cubic feet. And to my knowledge, there is no, because we need to do heating oil. I keep looking at this over and over. We're not doing natural gas. So we're not looking at natural gas, We're looking at this per gallon of heating oil, and we don't have a conversion in terms of gallons. To my knowledge, there's no way that cubic feet to gallon, I can look it up, but there's no cubic feet to gallon, like, oh, it's the same thing. Oh, it's half of it. It's nothing easy. So I'm going to look it up. I can't think of how else to do the problem outside of that. So I'll do cubic feet to gallons. And here we have this. We have 1 cubic foot is 7.48052 gallons. So let me write that. 1 cubic foot equals 7.48052 gallons. And now we currently have this 16 plus 4 pi cubic feet. 4 pi cubic feet. So we have to multiply 7 point whatever by that to get the number of gallons. All right, so we have 16 plus 4 pi. Let's multiply that by 7.48052. And we have 213, I mean, this is not exact, but I'm going to write it all out, 0.6913067 gallons. So that many gallons, we have a rate of 140,000 BTU per gallon. So 140,000 times this number would get me, times the number of gallons gets me the number of BTUs I can have. So let's do that. So that number times 140,000. This is the only way I know how to do the problem. I don't know what else to do here. It took me, I'm sitting on this thing forever saying, what do I do? So 299,167,82.94 BTU. Now, before we spoke in terms of millions of BTU, I think we can do that here. It's around 29.9 million BTU. Because I think that just makes more sense with regard to how we said it before. And that's just going to be my answer when it comes to the gallon talk. This problem kind of freaked me out a little bit. Yeah, this stuff isn't easy for me either. I mean, this isn't just welcome to IM3. They're posing problems, and they're not necessarily challenging. They're just kind of working things out in terms of unit conversions, and I'm not a fan favorite. Or it's not, not a fan favorite of mine. So, there you go. All right, I'm going to ditch number 12. Let's keep moving forward. Number 13. Making an argument. These are generally faster. As ocean depth increases, water molecules get pushed closer together due to the weight of the water above. Your friend says that the density of water increases as depth increases. Is your friend correct? Explain. Generally that's the case. That's what, happened to that submersible and stuff, depth of water and density and stuff. Yeah, it crushes it. As ocean depth increases, water molecules get pushed closer together. Yeah, you're packing in more water molecules per unit of volume. So your friend is correct. My friend is correct. Sometimes I'll type your friend and just kind of make that mistake. The more water molecules per unit of volume equals more density. Period. Yeah, water is denser there. You're packing more water. The weight of the water on top is really weighing that thing down as well. I guess. Yeah, do the weight of the water. Yeah, that works. I'm good. All right, number 14. Thought-provoking. You place 2 cans of regular soda and 2 cans of diet soda in a container full of water. The 2 regular cans sink, but the 2 diet cans float. Use the internet to research the contents of regular soda and diet soda, then make a conjecture about why diet cans float and regular cans sink. Include a discussion of density and buoyancy in your explanation. My biggest thing I'm going to say here is items that are denser will sink. Items that are less dense will float. We know that water was 1 gram per cubic centimeter or whatever. It was just 1. So if the other ones are different, if the regular soda should have greater than 1 gram per cubic centimeter of density, and diet soda should have less than 1 gram per cubic centimeter of density. And buoyancy is based on that comparison, compared to water at least. So let's research that one. Give me a second here. Regular diet soda. Regular soda. Sure, versus diet soda. Well, I just want nutrition. Let's see. Okay, versus diet soda. I'm just gonna say density. Density of a can of regular soda is just over 1 gram per cubic centimeter, whilst a can of diet soda is just under. That works for me. See, they say soda. I was going to say, what about the different kinds that we have? Coke, Pepsi, things like that. But yeah, they just say that over 1 and less 1. So here's one for Diet Coke, for example. 0.911 gram per milliliters cubic centimeter, and 1.026 gram per milliliter. So just more and just less. So that kind of answers it right there. So let me go back and start addressing that here. Number 14. Regular soda. Hold on. Regular soda. Sody. Regular soda is greater than 1 gram per cubic centimeter or cubic milliliter, whatever. Diet soda is less than 1 gram per cubic centimeter, and water equals 1 gram per cubic centimeter. So now I'm going to type out the rest here, just to speak on buoyancy. Buoyancy, I can't spell it, is based on the comparison of densities of objects. Because regular soda has greater density than water, a regular soda can will sink. Because diet soda has less density than water, a diet soda can will float. That's basically it. That's basically the idea. Thank you, Internet. Okay, and the final question is in number 15. Links of a chain are made from cylindrical metal rods with a diameter of 6 millimeters. The density of the metal is about 8 grams per cubic centimeter. And we have a picture. I think I want to copy paste this because I want to make sense of the cylindrical portion for you guys instead of drawing it myself. You know, these are, I mean, it's not a 2D, it's a 2D drawing, but imagine that you have cylinders here, right? So let's say, probably have to do something with volume, right? So, you know, this thing is made into like a cylindrical portion right there. You know, the whole thing's cylindrical, right? Chains, cylindrical. But this one part is just a cylinder in and of itself. And then you have, I guess, it's not a part of a sphere. I guess it's a bent cylinder. You have a bent cylinder here, but the same thing on the other side. So you have a couple cylinders here that you can double up. You have a couple cylinders here you can double up, that kind of thing. Anyway, cylindrical. They also show the density right here, 8 grams per cubic centimeter. Oh, now this is in millimeters, right? So 10 millimeters is 1 centimeter. The other way around, divided by 10. So you get 2.7 centimeters. I'm going to go straight to this right now. 2.7 centimeters. I don't know how this is going to be used at 0.9 centimeters and 0.15 centimeters, whatever that stuff is. What else did they say? Where's the diameter? 6 millimeters. So diameter, radius is 3.3 centimeters. Let me do that again. 0.3 centimeters. Okay, so there's a lot to take in. To approximate the length of a rod used to make a link, should you use the perimeter around the inside of the link, the outside, the average of these perimeters? Explain your reasoning. Then approximate the mass of a chain with 1,000 links. So I guess part of that, I guess that's what the 0.9 and the 0.15 are. Oh, it's not 0.15, it's 1.5. I guess what the idea of the 0.9 and the 1.5 here are for is the outside and the inside. I guess it's best, well, it's best in the cases of those three questions to average it. Find that average track going around here and around here. Now that's circumference based. The 27 is still, or 2.7 is still 2.7 here regardless. But if you find perimeter of the whole thing, That's those things plus circumferences, right? If I could take the chain link and unfold it into one chain, what do I have? I have a couple of my 2.7s here. Cross that out. A couple of my 2.7s here and here, and then I have a couple of these guys. Two of these would form one circle. But let's average those circumferences, right? So what is averaging 2 pi circumference? 2 pi 0.9 plus 2 pi 1.5 all divided by 2, averaged by adding these two circumferences and dividing by 2. Well, the 2's can kind of cancel. That's 0.9 plus 1.5. That's 2.4. So 2.4 pi centimeters is the distance of this plus this. And when I add that with the 2.7s, which don't have pi in it, perimeter is going to be 2.7s plus the 2.4 pi that's there. That's two of those together. So that's going to be 5.4 plus 2.4 pi. Whoops, pi centimeters. That is the, I guess, estimated perimeter around this thing when you average the 0.9 and the 0.5. Now, to do volume, see, now we're imagining that this is just one unfolded link, one unfolded chain. And it has a radius of 0.3 centimeters. So let's do volume by that, area of base times height. Volume is pi r squared times height, which is this entire length that we have here. So there's pi and pi. I think I can't do it in terms of pi without having a pi squared here. I might have to just give you the approximated value of this one. So let's see. 0.3 squared is 0.09, but 0.3 squared times 5.4 plus 2.4 pi times, oh, I never squared it. Hold on. You can't see my calculator, sorry. Squared times that times pi. And I'm getting 3.65. This is one link. 3.659. I'm rounding this. I won't round it in my calculator, but cubic centimeters. Now, we have to be in centimeters for this thing because the density is 8 grams per cubic centimeter. If we need to find the mass of a chain with 1,000 links, mass of 100 links, mass of 100 links, we have to take the mass of one of them, take this times 8, and multiply that by 100, basically. So I have those three things together. Let's do times 800. That number I had times 800. Now I'm getting about 2926.918864. So, did they say what to round to? No. 2926.92 grams per 100 links. So that's going to be the mass of those if I average those things. And that makes sense to do so. The outside track and the inside track will take the kind of the halfway point between that distance. I think that's going to make most sense there. That's part A. I don't know where part A starts. Let's pretend it's right there. Part B says approximate the length of a taut chain with 100 links. Explain your procedure. Excuse me. I don't know what a taut chain is. I guess they mean when the chains are interconnected like this, because now that length isn't so obvious. It's not just like 27. Well, I said explain your procedure, so there's probably multiple things we can do. So if I have this idea, right, I can almost copy paste that. Can I still paste that thing? Yes, I can. So if I have like this one, let me shrink it. All right, let's see. Copy, paste, boom, and it like connected like that, and copy, paste. You know what I mean? This would be the idea of the taut chain thing, I think. So let's get several of those, and let's get a procedure out from here. 27, I'll say this. My guess is 27 goes as far as, well, that's not necessarily true. I was going to say 27 goes as far as where this thing sticks out, but that's not necessarily true. We have the circumference of the inner track, or the outer track. Let's do this. Let's find out the length of every link in and of itself. Let's just find out what this length is from here to here and we'll take away the overlap afterward. So the length of any one of these is, what do they want? Millimeters? Or I'm gonna use millimeters. I might go to centimeters later, but we don't have to do any math stuff. So 27 millimeters plus we basically have the circumference. No, not the circumference. The radius, that 1.5 here and there. So plus two 1.5s, which would be 30. That's 30 millimeters per chain. Right? 27 to 1.5. I think it's 30 millimeters per chain. Now there are 100 chains, which is 3,000 millimeters. Now there's quite a bit of overlap here that we have to consider. The overlap, how many millimeters? Diameter was 0.6. So if this is 0.6 here and this is 0.6 here, we got to take away the 0.6s that are overlapped. Now keep in mind, the end chains won't have that overlap. Let's say this was the very end chain right here. There's no overlap on that one. This one has overlap and this one has overlap. So the end ones don't. And how many links are there? 100 chains. 99. There are 99 of these things that we have to take out. So we subtract 99 of doubling 0.6, right? If the diameter of each chain is 0.6 and there are two of them stacked on top of each other and we got to take that out, I want to make sure that's considered for all of them. Hold on. The 30, each link is 30 and we take out, yeah, I think so. I don't know. 99 to 2.16. Let's see how that turns out as just a number. If it's negative, I know I did something wrong. 99 times 2 times 0.6, and then do 3,000 minus that. 3,000 minus that number. And I'm getting 2,881.2. That would be millimeters. Let me think about that. 30 millimeters for each one. Oh, hold on a second. I said 1.5. That's not 1.5. That's 15. 1.5 was with centimeters at the time. So that's not 30 anymore. Let me do that again. That's 57. 30 plus 27, that's 57 millimeters times 100 is 5,700 millimeters. Is that right? So that's not 0.6 either, right? That's 6. Am I doing centimeters or millimeters? That's my problem. Right now I'm doing millimeters. I'll convert it centimeters as well. You just have to divide by 10, I think. So let's do that. 5,700 minus 99 times 12. 5,700 minus 99 times 12. And I'm getting 4,512. Would that be right? Double those, 99 of those linked 4,512. 27, two 15s added together. It's 57 millimeters times 100. It's 5,700 millimeters. Okay, I think that'll be it. So, boom, millimeters there. Sorry, I'm slow going through this. I was turning things into decimals when I shouldn't have. Now that's in millimeters. That would be, if you divide that by 10, that's 451.2 centimeters. I want to make sure that's right. I'm just looking through the things. I'm thinking if that 99 is right, and I think so. It'd be 99 links. If there are two links, if there are two chains, there's one link in between. If there are 3 chains, there are 2 links in between. That's kind of where I was going next. So I'm going to go with that as a final answer, assuming that's what taught means. Suddenly, I'm not thinking if that is, but I think that they would describe it if we needed to. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. I know there were some hiccups here and there, but I think I got through it correctly. So let me know if you do have any other questions with this. This can get a little weird. There was that one that had the oil, the heating oil and stuff like that. I had some trouble too, man. This can have some little issues here and there. But guys, take care. Thank you so much. I will see you in the next one.